So she is right. The point is, she is right, but there is something more subtle that she has glossed over. She is right in that the number of tokens is finite. Right? Number of tokens is not infinite. A token class itself may be infinite. Number of identifiers is infinite. But as far as parser is concerned, parser wants to know only that it's an identifier. Right? So number of tokens is finite. Right? Does that imply that the number of relationships is finite? Yes or no? No. So once again we got into infinity. Number of relationships is infinite. Now how do we handle it? Okay. Any other opinion? Yeah. You can continue setting. Yeah.
Can we like set a few of the relationships to be defined and we just say all the other ones are undefined?
If they're undefined, then how do you compile those programs?
By using the ones that are either we try to make it so that we can make these other relationships using the ones we already have, or we say that it's invalid syntax.
Okay. Any other guess? So this statement that number of relationships can be infinite is a very nuanced statement. You have to examine it more closely. So let's take an example. So I can declare variables. So I have int a comma b comma c. So I have declaration which consists of integers followed by a list of variables. There is no bound on the list of variables. So I can have one syntax tree which has one variable. I can have another syntax tree in which there are two variables. I have another syntax tree which has three variables. So there are possibly infinitely many syntax trees. How does the compiler deal with it? So even though there are possibly infinitely many syntax trees, the structure is still finite. What is the structure? The structure is, I can describe the structure of a type declaration in the following way. Let's take the simplest case of declaring integers. So I can say my declaration, so I have multiple declarations which can be, so the thing that we are trying to do is, we are saying I have multiple declarations which consists of a single declaration which consists of multiple declarations. So it's a list of declarations, single declaration followed by multiple declarations. Now I can have this declaration here and then I have declarations here. Like this, the tree can grow infinitely, right? And now in declaration, I can have, let's say, maybe I should have taken a single declaration. So I have, let's say int declaration. Let me use a different tree. So that will be much easier to understand. Let me take a smaller this thing. So for simplicity, let's call it int decl, okay, which has a type specifier and I have a list. List is a variable followed by a comma followed by a list. This list is also variable followed by a comma followed by a list. Right? Now this list can keep growing. So there are infinitely many possible parse trees. But observe that this structure is same as this structure. There is no difference between them. Yeah. They can't? You're not able to see the board. Where do I move so that you can see the board? Can we keep it here? Yeah, maybe we can just keep it here. Okay. Yeah, we can have it there. Yeah, maybe. Yeah, yeah. Thank you. So the point is that this structure and this structure is still same. It's repetition of the same thing. So I may have this structure appearing infinitely many times, but the structure itself is fixed, right? Now I can say in the end, maybe list is just a variable. So I can describe it this way. So I can describe it in the following way. I can say I have integer declarations which consists of type followed by a list. And how does a list look like? List is either a variable or another list, or list is just a variable, right? These three rules are sufficient. These three rules are sufficient to derive all possible infinitely many declarations. Because I am writing this rule recursively. List can be a variable followed by list. Now I can expand this list to any which way I want. And this is the base case of the recursion. Eventually it terminates with variable. So although the number of parse trees can be infinite, number of tokens is finite, but number of parse trees is infinite, we can still describe all possible parse trees using this device. And this device is nothing but a context-free grammar. This is a grammar. So I have a non-terminal here. I forgot to write type. So maybe type is an integer. And then I can say type derives integer, or I can say type derives float. Okay. So the point is that although there are infinitely many possible parse trees, the rule of constructing those parse trees is finite. The number of rules is not infinite. So that is the hope that we can actually write a parser, right? So parser has to know these rules. It does not have to know the trees. So yeah, is list derives var. So here var is a terminal and list is a non-terminal. Question is, which of these are terminals and which of these are non-terminals? So rule of thumb is all leaf nodes of a parse tree are terminals and all non-leaf nodes of the parse tree are non-terminals. Right? So when we talk about parser, we have to know this is a grammar, a context-free grammar. So context-free grammar is a finite representation of possibly infinitely many trees, right? So what we do is this is a formal representation. Now we can have a system which takes this as an input. Now I don't have to worry about infinitely many programs. because I have written the rules using which these infinitely many programs can be constructed. That set of rules is finite. All I have to do is to keep invoking the same rule as many times as I want. Now the next question is, if I can invoke the same rule as many times as I want, how do I know this process of invoking rules will terminate? Can it not go infinitely many times? How? Why? Yeah, so I'm saying, how do you rule out that possibility? Okay. Anyone else? Yeah. Okay. Any other question? How do I know that the derivations, that how many times do I invoke the rule, that is finite? There is no bound on how, there is no bound on the number of variables in a list. Exactly. The program that we submit to a compiler has to be finite. You can't write an infinitely large program. A program may run for an infinite number of seconds. You might write an infinite loop, but the program text is finite. Hello, hello. The program text is finite. So therefore, you will never invoke this infinitely many times because you cannot write an infinitely large program. Because every program is finite, number of rules is finite, so therefore you can derive infinitely many sparse trees. So you can have infinitely many programs, but every program has to be finite, right? So these are the issues. I'm just trying to show you the kind of conceptual issues that compilers have to grapple with and how we overcome these problems, right? Okay. So that was a long introduction to what's going to come. So we're saying this structure is represented by a parse tree. If the parse tree can be constructed, input is syntactically valid. Now, why did I take this detour? I took this detour because there is a question. If a parse tree can be constructed, now there are three possibilities. Either a parse tree can be constructed, yes, or parse tree is not constructed because there is an error, or parse tree is not constructed because we have to take infinitely many steps. Third possibility does not exist. Either you are able to construct a parse tree or you cannot construct a parse tree. As simple as that. There's no question of I don't know when to stop, will I keep going forever. That situation would not arise. So therefore, a parser can tell you, no matter, you may submit infinitely many programs to a compiler one after the other. You can't say, you don't say that compiler can be used only finitely many number of times and after that it wears off and loses energy or whatever. There is no loss of energy with the compiler. So you can continue to use it as many times. There is no bound on the number of times you can use a compiler. There is no bound on the number of programs that you can submit to a compiler one after the other. But the point is, we will always be able to say, yes, this program has the right syntax, or no, this program does not have the right syntax. Okay? So we might decide that the program is syntactically valid, but it may not be semantically valid, and we'll see examples of that. Okay? So a description of syntax should be unambiguous, correct, complete, and convenient for use by the designers and implementers of a language. We can't give a syntax description which covers 99% of programs. We want syntax description which covers 100% of programs. There's nothing like this compiler is superior to that compiler because that covers 98% and this covers 99%. That's not possible, right? So this, a context-free grammar meets this requirement. This is an example of a context-free grammar. a finite representation of possibly infinitely many syntax trees. Right? That's the point of this slide. Okay, so where is the place of a parser? We have seen typically it's always a parser driven compiler. Every compiler, the front end is a parser driven. Sometimes we might have parser generating code directly. That used to be the case earlier, but not anymore. We have a parser which drives the front end. We have seen this again and again. This is the most common organization. Okay. Now let's talk about the notion of derivation. I use the word derivation. I said that we can derive this syntax tree from, we can derive infinitely many trees from a set of finite rules. How do we derive it? We derive it by replacing a non-terminal by the right hand side of a production. So all these rules, each of these rules is called a production. A grammar rule is a production because you can produce a larger structure using these rules. You are allowed to replace a non-terminal by appropriate right hand side any number of times. And the question is, how do you know which is the appropriate right hand side? That is where the parsing algorithms come into place. Okay, a parsing algorithm will determine, will choose. Obviously, number of right hand sides is finite. Parsing algorithm will determine what is the right hand side to invoke to replace, and that determines which parser is more powerful. Sometimes a parser may declare programs to be ill-formed if the parser is not powerful enough. There are various categories of parsers, parsing algorithms, but we are not going to go into those details. But I'm saying there's a large variety of. The critical discussion in a parser is so let's say you start constructing this tree int type list. After that, do you invoke this rule or do you invoke this rule? Both these rules begin with var. How do you know which rule are you invoking? So that's where some very beautiful ideas of parsing algorithms come in, and unfortunately we do not have time to go into those details. Okay, so so consider the following grammar of expressions, which says E is an expression, E plus T is a term, and F is a factor. Okay, this is a grammar that's given. A possible, so this is called a derivation. So I replace E by the right hand side E plus T. Now I can replace this E by T. Now I can replace this T by F. Now I can replace this F by ID. Why can I replace F by ID? Because I have a rule which says F can derive ID. Right? So I have ID plus T. Now I have ID plus, now this T can be derived as T derives F. So I can replace this T by F. Then I can say this F derives ID. Now I can say this F derives ID. That is how I derive a sentence given. So I'm supposed to, this is the input and this input is derivable from the start symbol. Therefore, this input is syntactically valid. And as you can see, try it yourself. There is exactly one way of deriving this input from this set of rules. You cannot have any other way. If you try to do some other replacement, you will get stuck somewhere. That's the beauty of parsing. Parsing is deterministic and predictable. Right? But we will see the situations when we can run into problems. Okay? So now there's this notion of rightmost derivation and leftmost derivation. What is a derivation? A derivation is replacing a non-terminal by some right-hand side. How do we know what right-hand side? Parser has the knowledge, parsing algorithm has the knowledge. We will intuitively look at how it knows to do that. Depends on the input sequence of tokens. Okay, so we want to derive a non-terminal by some right-hand side. There could be multiple non-terminals in a rule, right? How do I choose the non-terminal to derive? I can pick up any arbitrary rule. So therefore, in order to make things predictable, we choose, okay, we will derive always either the leftmost derivation or leftmost non-terminal, or we will always derive the rightmost non-terminal. So for the same sentence, ID plus ID star ID, let's look at this derivation. This is the leftmost derivation. So I am saying E derives E plus T, which means we are constructing this parse tree, E derives E plus T. You can see with every derivation step, we are making the parse tree larger, right? Now, we are saying this is leftmost derivation. So, what will we derive now? In this, we have E plus T. Will we derive E or will we derive T? E, because it's leftmost derivation. So, we say, okay, we derive E. Okay, so we derive T. Okay, so this is T plus T. E can derive either, so E has two possibilities. I can derive either E as E plus T or I can derive E as only T. I chose to derive T here. Can you tell me what was that choice governed by? But what would have, if, would things have gone wrong if I have derived E plus T? So if I were to replace this E by E plus T, would it be right or would it be wrong? Right? Wrong. How many people say it's right? Please raise your hands. One, two, three. How many people? Three and a half. Okay. Just raising hand half-heartedly. How many people think that it is wrong? And why do you think it is wrong? Okay. Any other explanation? So what's the problem? Let it increase. Yes. The input given to me has only one plus. I don't have two pluses. Right? So if I choose that rule plus t, I will get two pluses. And then I won't be able to derive this sentence. No matter what parse tree I construct, I am not going to get this. This gives you some idea of how a parser can determine what is the right hand side, what is the rule to derive. So assume that there is a very beautiful theory, but I love this theory, but unfortunately I can't go into the details. I spent about 3 lectures or maybe 6 lectures, 2 weeks on talking about how do parsers decide which rule to pick up. Very beautiful, nice formalisms. But let's go ahead. So now we know that we have to derive T. Now T can derive F or T can derive T star F. What should we use? Just F or T star F? Uh-huh. T star F. Some people say T star F. Uh-huh. No, I'm just this. We are doing leftmost derivation, so we will derive this T. That's just F. Fine. So we have F. Okay. Now this F again we have to derive this. We are talking leftmost derivation. So this will derive ID. Remember, at every step there is exactly unique choice. Once you fix which non-terminal to derive, you don't have too many choices. There is exactly one choice. Okay. Now we have a single non-terminal. Now we derive this T. What can we derive it with? F or T star F? T star F because we want a star there. Right? So we make T star F. Now what will we derive? Now we have to derive this T. This is the symbol that we have to derive. Right? So this will be F. We can't have T star F because there is only one multiplication. Right? So we derive this as F. Once again we are doing leftmost derivation. So we will derive this F. What will it derive? What will? Just ID. Right? And now we have this. So that gives us ID. There is exactly one way of constructing a parse tree, exactly one leftmost derivation of a parse tree. But we can also have a rightmost derivation. For example, we can say, so this is top-down, left-to-right construction of parse tree. Now I can do rightmost derivation. So I will, what will I derive here now on the right hand side? T. And what will I derive it with? T star F. Good, very good. So now you have become intelligent enough. Now, what will I derive now? F. What will I derive it with? F has only one right hand side. So there is no choice. So we have ID, right? And now what is the next symbol that I'll derive? T. And what will I derive it with? F. Very good. Now I have to derive F. So it will be ID. Now I am left with E. What do I derive? T, because I can't take E plus T. So I derive E T. Now T will derive F. F will derive ID. There is exactly one leftmost derivation or exactly one rightmost derivation for a parse tree with this language, with this grammar, right? Now, does it happen always? Can there be a situation that maybe there are multiple ways? Depends on the grammar, depends on how you write the grammar. For example, I may have this grammar, A plus A, right? Now I can do many things. So for example, I can say, I don't think I have that on the slide. I wish I had it on the slides, but let's do it here. Okay. So I can say, let's say I take this ID plus ID star ID. So I will not do the entire derivation, but I'll give you parse trees. So I can say E derives E plus E with this new grammar. Okay. And now I can say this derives E star E. Okay. This derives ID. This derives ID. This there's a terminal. This derives ID. But this is not the only way. I can say E derives E star E, and I can say E derives E plus E, and now I can say this is ID, this is ID, and this is ID. I can write it this way. So the point is, am I grouping this or am I grouping ID plus ID star ID? That is the question, right? This parse tree does this grouping, this parse tree does this grouping. So depending upon the grammar, you might have multiple leftmost or multiple rightmost derivations, and therefore you may have multiple parse trees. Such grammars are called ambiguous. They're called ambiguous because multiple trees are possible, multiple structures are possible. Now you will appreciate why I should separate plus and star as a different token. If I separate them as different token, then my parser can choose which rule to use. Okay? How does a parser generator handle these things? Beyond the scope of what we are doing, but I just want to convey the notion of ambiguous grammar. Okay, so we have, oh yeah, I do have these two derivations. So these two different parse trees, right? I can have, so we can disambiguate this grammar. We basically give a higher precedence to star than plus, make both of them a left associative, and that gives us disambiguated grammar. So every precedence level is given a different non-terminal, in which case there is no confusion. Then the grammar becomes unambiguous. Similarly, the if then else grammar is also ambiguous. I will not go into the details. The idea is, does the else associate with outer if or does it associate with inner if? That's the question. So you can have two different parse trees for the same thing, and this grammar is ambiguous. So we require unambiguous grammars. If we specify ambiguous grammars, then we have to somehow tell a parser generator what is the right rule there. And there are some nice ways of specifying that, but I will not go into the details. Right? So again, how do we disambiguate this grammar? But let's not go into the details. So this is the main thing of the parsing that I wanted to convey. There is a notion of a context-free grammar. It can help us generate as many parse trees as possible, but we have to be careful about ambiguous grammars. That's the story that I am going to tell you. Before I proceed to semantic analysis, any questions? Does this seem okay? Okay, so let us see. So the role of semantic analysis is establishing semantic validity. So we have determined syntactic validity. Now we want to determine semantic validity. So we have to talk about what kind of errors are possible in the program, what kind of analysis can check these errors. The other application of semantic analysis is to generate intermediate code, either AST or a 3 code, and generating code for runtime support. How do I handle procedure calls and returns? Okay. So let me just skip this part. This is just getting into details. So how do we perform semantic analysis? So using context-sensitive grammars is expensive. So compilers use rules associated with context-free grammars to perform semantic analysis. I don't think we will go into too many details here. So in order to ensure validity, we have to discover, detect and prohibit errors. So we have shown this schematic. Remember, we have shown scanner and parser, but they happen in a interleaved manner, which is for clarity. We have shown, for simplicity, we have shown them sequential. So you have a scanner, you have a parser, you have semantic analyzer, and then you have a optimizer, and then you have a code generator. Eventually, you have a linker, and then you run the program on the machine with runtime support. This is the entire stack of running a program. Getting an executable version of a program through a compiler tool chain. So the errors that are discovered in the green part, they are compile time errors. Okay, so when you are compiling a program, there are errors. Okay, these are called compile time errors. The errors that you get at link time are when a linker flags an error, it's a linker error. And then runtime error is execution error when the execution fails. So what are the compilation errors? Either there's a lexical error, which is, for example, non-terminating comment, non-terminating string, use of an illegal character. These are examples of lexical errors. Or there's a syntax error in the sense that you have given a sentence which does not derive from the given uh, 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 grammar. For example, you could write ID plus ID is equal to ID plus ID. That's not allowed. On the left hand side, you should have just one ID. That can't be derived using the grammar. So these are syntax errors. And then there are semantic errors which are discovered by semantic analyzer, and even optimizers can discover semantic errors. Okay. In the case of link time errors, you have missing functions, you have missing global variables, and then you get, for example, in C++, you get this message, undefined reference to table for F. Now, F is a class, you have a class hierarchy, and there is something, F is a function in a class hierarchy of the classes, it's possibly a virtual function, and some class in the class hierarchy hasn't defined F. So table is called virtual table. So you are unable to create virtual table for all classes in the class hierarchy. Now that's a link time error. Okay. And runtime error could be of two kinds. Logical error where execution completes but gives wrong result, or there is the undefined behavior, execution either aborts or give you wrong results. Okay. So where are these undefined behavior versus unspecified behavior? Again, I don't want to go into too many details because it's more of an information rather than concept, and giving information in a lecture is boring. It's there on the slides, you can pick it up and ask me questions. But you have to understand the difference between undefined behavior and unspecified behavior. Undefined behavior is unchecked behavior. When it's undefined, if you write a program with undefined behavior, it's not the responsibility of the compiler to do anything. No responsibility of the compiler or its runtime support. It may have unpredictable outcomes, execution may abort or give unspecified result, and a compiler is legally free to do anything, okay, including formatting your hard disk or generating code to release a missile. If a compiler does it, legally compiler is still right because you submitted a program with undefined behavior. It's your responsibility. Unspecified behavior, and we will see examples where compiler can do some reasonable choices, but the language doesn't say what should happen. So it's compiler dependent behavior. Okay. So available choices may not affect the result, but may influence efficiency. So for example, the order of evaluation of arguments to a function. So you have, or you have sub expression. You have an expression consisting of E1 plus E2. Do you evaluate E1 first or E2 first? That's an unspecified behavior. Okay. Compiler doesn't, language doesn't say do this or that. It's left to the compiler. And then you can get into funny situations when you have plus plus appearing here. Even that is not defined by the language. Every compiler chooses how to generate code for it. One of the reasons why people say don't write programs with plus plus embedded or minus minus embedded anywhere in the expression is it's an unspecified behavior. Different compilers may produce programs that may produce different results. It's very instructive to see how does GCC, for example, handle plus plus. There's a fixed way. Every compiler decides. It's not undefined. It is unspecified. Left to the compiler to deal with it. And exceptions are the prohibited behavior checked by the runtime support. Okay. So when you have undefined behavior, of course, practical compilers won't format your hard disk. Practical compilers would do something more meaningful. Typically, they would detect and issue warnings. All warnings arise out of undefined behavior. Okay, these are not errors. Compiler won't say, "I don't compile your program," but compiler will say, "Here's an undefined behavior. I don't know what to do it. You better take care of it." Okay. When you have unspecified behavior, compiler can make choices based on well-defined criteria, based on the wisdom of the compiler writer. And in case of exceptions, compilers try to detect these at compile time or at runtime. Okay. So Java follows the exception approach for predictability, where C and C++ follow the undefined behavior for efficiency. Okay, so some examples of undefined behavior. All memory violations are undefined. Dereferencing a null pointer, out of bound array access, modifying a string literal in the program, accessing uninitialized variables, invalid pointer arithmetic, using a pointer after free, dangling pointer, accessing local variables after function return. These are all undefined behaviors. So these are memory violations. Undefined behavior may have compute violations. Division by zero, sign integer overflow, overflow or underflow in floating point operations, failing to return value from a non-void function. Maybe you have a path, a function is supposed to return integer, but there's one path where it doesn't return anything. Or maybe there's an infinite recursion without a base case. So all these examples that can occur. There are many more examples. I have just picked up a small number of representative examples. Unspecified. So this is undefined behavior. Examples of unspecified behavior. Order of evaluation of function arguments. In which order should the arguments be evaluated? That is unspecified. And therefore, never do a plus plus to an actual argument in a function call, because you don't know what will happen. Order of evaluation of sub-expressions. Never do a plus plus inside of a sub-expression. Overflow, alignment of structures in union, that's unspecified behavior. Do they align at 8-byte boundary? Do they align at 4-byte boundary? Do they align at byte boundary? That is unspecified. Every compiler will decide what to choose. Memory layout of struct and union. Padding added to structures. These are examples of unspecified behavior in C. Every compiler will decide what to do. So we will stop with this, I think. So semantic analysis is used for three things, broadly speaking: validation, of the input, generating IR or optimizations. For the purpose of validation, there may be runtime validation or there may be compile time validation. Compile time validation may be over a concrete or abstract syntax tree, or it could be over control flow graph. We have seen the examples of control flow graphs. So over concrete or abstract syntax tree, we do things called declaration processing, name and scope analysis, type analysis, interesting things, but beyond the scope of this winter school. Over control flow graph, we do data flow analysis for discovering return-free paths, uninitialized variables, null dereference, etc. We will see introduction to data flow analysis tomorrow over control flow graph. And for optimization, so at runtime we have dynamic typing, exception handling. For IR code generation, you could generate abstract syntax tree or tree address code in the form of a control flow graph for handling procedure code for handling procedure calls. Optimizations typically happen over control flow graph. So this is the entire canvas of semantic analysis. There's just one last slide that I want to show here, which is how can a compiler ensure runtime validation. So this is a compile time activity. We're doing something at compile time. Program is going to be executed later. So what can compiler do? Compiler can ensure checks like this. For example, if I want to generate a code, I want to give a compiler which never aborts because of a null pointer exception. I can generate this code. If x is null, if x is not null, if x is not null, return the value of x, otherwise just complain. So I can insert this code. This is the example of runtime validation performed by the code generated by a compiler. But as you can see, this could be expensive because even when x is not null, this check will happen at runtime. So C compilers don't do that. But we could write a program like this, do a program analysis and say, at this place I know x is not null, so I don't need this check. That's an example of an optimization. Eliminating redundant checks. A redundant check could be for null pointer exception, could be for whatever can happen at maybe zero division error. Maybe I want to check whether this value is zero. In some cases, I may be able to say that this check is not required. So all this comes as a part of program analysis, something that we are going to talk about. So with that, we come to the end of compiler front end. If you have any questions, I would like to take them now. Yeah. The question is what exactly is a linker? So C and C++ allow programs to be written in multiple files. The entire program doesn't have to be in one file. So I may have main function in file F1. I may have main function may call another function called compute, which is defined in F2. Now when I generate the program, I have to know what is the code of compute. So a linker puts together all translation units, entire code, and identifies external references which could be calls to functions that are defined in some other file, or use of variables that have been declared in some other file. Linking in one sentence is resolving external references. This could be data defined in some other file, or this could be functions defined in some other file. That's linking, because you compile one file at a time. Uh-huh. Okay, so I'll give you a thumb rule. Whenever you have a question like this, ask yourself the following question. At what time do you expect this activity to happen? Do you expect it to happen when you're writing the program? Do you expect it to happen when you're writing a compiler? When you are, do you expect it to happen when you are compiling a program through a compiler that has been written? Do you expect it to happen when you are executing the compiled program? So this, when do you expect to happen? At the time of execution, and so compiler has nothing to do with it, right? External references within the program. So I have declared a variable. Its declaration is not in this file, it's in some other file. I'm calling a function, it's not defined in this file, it's in some other file. So linker will go and find it out. That's the link. Yeah. Mhm. So the question is, how does semantic analysis happen in case of types that are dynamic, which are discovered at compile time? Would anyone like to hazard a guess? I'll give you a clue. We have just seen one slide that tells you how it can be done. Uh-huh. No, but it's dynamic. It can change at runtime. No, but compilation has happened. We don't have the tree now. We don't have the parse tree. We don't have semantic analysis the way we are talking about it. The clue is the following. The way it can insert a check, it can insert a type check, it can insert a code to check the type at runtime, right? So compiler will not do itself, compiler will not do the check itself, but compiler will insert a code that will do the check. Not type allocation, dynamic type analysis. Okay. Any other questions? If no questions, then I would like you to get on with the experiments. I'll show you what you have to do, and you have to access this drive. Go to day one, introduction to compiler frontends. There are these tutorial problems which we will come to. So I have some pen and paper exercises. So this is about control flow graphs. So you have been given some piece of code. You have to read and draw the control flow graphs. The TAs, Nisha and Rohit will help you with it. But first, I want you to run these things. Uh, Visualization. So you have this, look at this readme, and you have been given programs. Try to see for each program, see its parse tree, see its control flow graph, and see its SSA. SSA is something we are not going to talk about today. Professor Amey Karkare will talk about SSA on day 3 or maybe day 4, depending on what his plan is. So are you all able to access the Google Drive? Please do that. Please construct the ASTs, the parse trees, and show me, explain to me what parse tree you have constructed. Ask Nisha, ask Rohit, ask me. Nisha and Rohit, you should come here in front. So they'll call you. If you remain at the back, no one will ask you anything. I want each one of you to be able to run these things. Okay, so I have just now made up a rule. Those of you who show me your AST, me or Nisha or Rohit, your AST, a pass tree, and your CFG, you are allowed to take the tea at 3:30. Others are not. No break for you if you don't show us the pass tree and the control flow graph for at least three programs, three or four programs. Which is it's not Wi-Fi on my phone. Yeah, thanks. There's a mobile signal in this room. Yeah. Yeah. Yeah, now I can see messages coming. Thanks. So I want you to observe the parse tree and the control flow graph for every given program. And when I say observe, you should be able to explain why do you have this node here, why do you have that statement here, how does it relate to the input program. That's the thing that I want you to observe. Nisha? Which program is this? Oh, so it's a huge parse tree, is it?